make sure it is recording. It's all good. Cool. Oh, closed the wrong tab. There we go. Okay. So I'm not sure where I ended with this class last Wednesday. Did we start to talk about coding a little bit?
You showed us a little bit. You went over the instruction set.
Instruction set? Okay. Yeah. So let's start with the instruction set again and see if I can answer any questions, assuming you guys did some studying over the weekend. You at least looked into this whole thing. All right, so the share folder is open to everyone, and you want to go to the processor subfolder, and there are several documents that you want to kind of pay attention to. One is the assembler manual. The assembler manual is intended to be kind of like a introduction to use the assembler itself, as well as it describes all the instructions. Did I go through at least one sample program on last Wednesday?
Yeah.
In this class? I did? Okay. Is that the find maximum one? Or something simpler? No. Simpler.
Something extremely simple.
Okay, cool. Not a problem. So what we'll do today is we'll start with something that is a little bit more complicated, and we'll see how to do it, convert a C code into assembly code step by step. So what I'll do is I'm going to do it by Notepad first. We'll just look at the C code, or pseudo C code for the most part. And this is for finding the maximum, okay? So I'll present the code first. And in this case, all of these are registers. So we're dealing with values already stored in registers. We're not so concerned about how do we get those values into the registers first. We'll just say that, okay, we have some values in the registers. So, but we do want to specify the logic of if A is less than B, then we want C, which is the maximum, to store the value of B, because we want to find the maximum of the two. Else, okay, the else case is C, which is going to be the maximum, or whatever register we want to store the maximum is going to store the value of A. This is all we want to do. Okay. At this point, you can assume A, B, C are registers. So they're register A, register B, and register C. A and B are pre-initialized with certain values. And we just want to make sure this logic is implemented so that C always ends up with the maximum of the two. Is that okay? All right. So now the question is, how do we do this? Well, okay, first of all, I'm going to insert comments to every single line because we are ready to turn this into assembly code. I don't want to lose the C code because the C code is useful. It tells me what the program is supposed to do. So what I really want to do is to interleave my assembly code with the C code so that I can see, okay, this line of C code translates to this line, these lines of assembly code, and so on. And you can always start with the simple ones, okay? C gets the value of B, sounds like copying the register of a register, and that's done by CPR, okay? So CPR is what we want, and when you look at the CPR instruction, it says X equals Y, so in this case, because we want C equals B, C needs to be the first operand, and B needs to be the second operand. Is that okay? All right? And then over here, we do the same thing, CPR, CA, like that. Now, if you're not really sure whether the CPR instruction does that copying from right to left, one thing you can do is to write a very simple one-line program, 2 lines, okay? Run it in LogicSim and make sure that the program does what it is supposed to do, okay? And then the other thing that you also might want to do, okay, I'm going to do it. So instead of just suggesting that you guys do it, I'll do it. So we'll go ahead and go to the assembler, which is an actual assembler. You go to the tab labeled source to write your code. Now, there's a whole bunch of code here already. We'll get rid of these. We don't need all this stuff here. Okay, it's okay to delete stuff in column A, but you do not want to insert columns or remove rows and stuff like that. Okay, it's okay to clear the content of column A, but don't do anything else. So you want to copy and code from a text editor into this spreadsheet. So what we want to do is we'll say CPR BA, okay, and then a halt instruction right after that. And you want to make sure that you don't get any errors here, because if you accidentally use something that is not a register, for instance, if you say register X here, it'll give you an error. It will say a register is expected and X is not a register. So You need to give it an actual register. And this is all we're going to do. You go to the RAM file tab. It gives you the actual output. So the first byte is 58. The second byte is 01. That's going to be our program. Go to File, Download As. Comma separated value will work fine. So we just name this one as CPR, okay, because that's what it's doing. And then you start at Logisim. And we can direct it to processor wdpc2.circ. So now we have the processor started up. First thing we do is to reset the processor first. And then we can right click on the RAM module, select load image, and then we go to the folder. I put it into the temp folder. So it's right here, cpr.csv, open. And now we have our program here, 5801. I know it's hard to read, but that's the content of RAM at this point. Okay, so the process is ready to execute instructions. Okay, now later on in the semester, I will just kind of zip through the whole thing and watch the effect of the program. But at this point of this class, if I were you, trying to study at this point, I would execute the instruction clock by clock. I would use Control-T to clock by clock go through this instruction. It's not as easy for me to do it here because my screen resolution is limited to begin with, and I can't really show you guys. These numbers are much harder to read when they're all on the same screen. But when I do a Control-T, okay, one more time, you can see the instruction itself, which is 58 in hexadecimal, is now stored in the instruction register. If I clock one more time, or two more time, it will be stored in a Ucode pointer. It is 580, that is here. And then the ROM will go to location 580. So this is the beginning of the actual instruction itself. In other words, the bit pattern coming out of the ROM right now is controlling the switches, the multiplexers, the demultiplexers. It is also enabling the registers, the related registers and whatnot, in order to carry out the operation. So this is a good time to examine, really examine. Stop the whole thing, don't Control-T anymore. Yep.
When you hit Control-T in there, it doesn't do up then down, it just does up, down, like once per click, right? Sometimes it felt like it was doing both, but I might have just been double clicking on it.
One is just a single edge. So okay. It will do rising edge.
Down, go up.
Yep. Okay. So it would go rising edge and then do it again, it would be falling edge.
Okay, I might have just been tapping it twice or something.
Yeah, you might be double tapping.
Like it was doing one and then sometimes it would do the other.
Okay. You might be just double tapping.
Yeah, I was going too fast.
Yep. But you can see, how input enable is light green here, which means register input is enabled. You can also see, how we select the input register. You can click on the wire. It will show you the content of the wire. I don't have enough zoom level here to do it, but if you zoom enough, you will see which register is being selected. You can also see the output register output 0 enable is turned on, which means this demultiplexer is driving the output. And then the channel that we are selecting is 10. This is 00, this is 01, this is 10. So this is the Y that is being driven with the content of the source register, and then it goes all the way back to here. Go to this mux. This mux has a selection of 0, so input 0 is selected to go into this line, which also means we are using the output of a particular register from the register bank to go back to the register bank, but the input side of it to update one of the other registers. But when you zoom in, you can actually see which register is going to be updated. So let me zoom in a little bit and click on this wire. Hopefully it will. Nope, still doesn't want it. Okay. If you do a right click and say view register bank, it will tell you which one is selected. It says right here, input register select is 10. So register C is getting updated. And when you look out here, register 0 is serving as the output. So we are using the value of register A to update the value of register C. But at this point, nothing happens because I'm just enabling it. We need a rising edge in order for this content to go into the register. Now you're not going to see anything because they have exactly the same thing. So you can actually always doctor the output of each register, the content of a register. Make this 7E, make this 87, so that this way when it does update, it'll be clear. The next clock will update it. Okay, so when I do a Control T, it's going to update it, like so. And you can zoom back out and look at the ROM module again. Look at the microcode pointer. The next clock is going to increment the microcode pointer. The next location of the microcode pointer is going to point to the content of 2 followed by all zeros. And what that 2 is going to do is to reset the microcode pointer itself because it connects to the reset port of the microcode pointer. So the microcode pointer will go all the way back to location 0, which means it is now ready to fetch the next instruction in and repeat the whole cycle. Is that okay? So I think it's not this class. On Thursday, somebody asked me, how do I study for this portion of this semester? This is how you study. I mean, because the book is here. The book is the open source version of the processor. It is already here. The question is, how do you study it? And to study it means you look at each instruction, you execute the instructions clock by clock so that you understand how the multiplexers and the demultiplexers and the enable of the registers, how do they work together in order to get something done. Is that okay? Because the written text version of what I described is going to be even more boring than the interactive one. And when you do this on your own, okay, it's basically how you study. It's like, okay, you can do the observation. Okay, in other words, you can say, pick a particular instruction. Go to that list of all the instructions. Go to the assembler manual. Pick one of these things. Okay, you go like, I want to look at this instruction here. How does it work? What does it do? Okay, you read the C code version, the C explanation. It seems to suggest that we are taking the value of a register X, which is the second, and we store the content of that register to whatever RAM location is pointed to by Y. That's basically the intention of this notation. Okay, how does it do it? You design an experiment to do it, okay? So if you want to go through the whole exercise, you can do the assembling yourself. Yep.
So that's not going to be copying it to register Y. If like register Y is 03, it's going to copy X into 03 in RAM.
Location 3 in RAM,
okay,
correct.
Cool.
Yep. And that's why there's a little asterisk here, which is the dereference symbol. And this is really kind of, it's just coincidental that Jake was talking about how pointers was an important concept in cisp 360, and this is why. This is why cisp 360 is a prerequisite of this class. It's because I rely on your understanding of pointers from that class in order to understand these operations in registers. And then somebody, okay, you don't have to raise your hand, but I know there are people who say, but I have forgotten everything about pointers. That's okay. Okay, even that is okay. Why? Because you can do it this way. So if you have forgotten everything about pointers, then what you can do is to say, I'm going to do a ST instruction here. I'm going to store something into what register B points to from register D. Okay, make sure you don't get any syntax or semantic error here. You go to the output, go to RAM file, the RAM file. It says FD01. I will just be lazy because to save the file and then upload and then download it and then open it on the other side, it's just a little bit longer than clicking the reset button first. Okay, remember you have to click the reset button in order to clear everything first, and then you go to the RAM content here, and you can just hand edit this. I think it was FD and then the 01 for the halt instruction. Okay, and let's just say that you have a kind of an idea of how this is done. So then you go to the registers and you change those things. So you go to the registers and you say, okay, let me see what was the instruction. D to B. Okay, so register D is supplying the content. We'll make it like 1, 3. And then register B controls which location in RAM is going to store the content. Let's make that 0, 6. Okay. So the result of executing the instruction should be location 6 should be changing from 0, 0, which is default, to 1, 3. Okay. But how is it done? So you go back to main and Control T so that we at least get to that instruction. So we are now fetching the instruction, which means at this point the instruction register. Whoops, one more click. So the instruction register has the content. How come it's not going to? Okay, let me try that one more time. Reset FD01. And we also want to change the registers. And we'll Control T. And the instruction register. Okay, now it's correct. So it's got FD. The next Control T will go to FD0, which is the location of the first slice of the microcode corresponding to the ST instruction. Okay. And the bit pattern coming out of the ROM is now directing all the switches, all the multiplexers, demultiplexers, and control lines for the RAM in order to perform this operation. So then you look at the rest of this design here. First of all, you look at RAM. It says the RAM module is now selected. In other words, okay, RAM module, pay attention, I'm talking to you. You look at the RAM load tunnel, it has a low value, which means it is a write operation. Then if it's a write operation, you want to know who is driving the data bus. Okay, you track down the data bus, and you go like, okay, several things can be driving it, including this particular demultiplexer. And when you look at this particular demultiplexer, the enable pin is turned on, which means this demultiplexer is in fact enabled. At this point, it is one of its output is being driven. But which output is getting driven? You click on this wire. It is the connection, the output called 1, 0. This is 0, 0. This is 0, 1. This is 1, 0. This is actually getting driven by the content here. But who is driving this wire? It is driven by whoever is selected as output 0. So you look at register output 0 select, which is this Y here. It is 1, 1, which is register D. So register D is driving the data bus. Who's driving the address bus? Who's specifying which location are we changing? So you locate the address wire and you say, okay, who's driving it? We know it's 5, but who's driving that? It goes to this particular multiplexer, which can select from one of its 2 inputs. The address mux is a 0, which means we're taking input 0 of this mux to become its output. Input 0 of the mux comes from the output of this demultiplexer. Who's driving this output 0 of this demultiplexer? The select pin says 0, which means output 0 of this demultiplexer is being driven. But where's the source? The source is coming from the register bank, output 1. But which register is serving as output 1? You look into register output 1 select, which is 0, 1, which means register B is the one that you have selected to drive that particular output of the register bank. So that is how you would study, okay, is to look at each instruction. When it executes, you look at the ROM output from the microcode engine, and you say, okay, which switch are we changing? Which switch is enabled? Which register is enabled? Which how are we selecting things from the register bank? Is the RAM getting addressed? Are we talking to the RAM, or are we even not using RAM at all? That is how you study for this particular processor. Is that okay? Now, if you look at add, let's say you understand how add works. Okay, do you have to do the same thing? Instruction by instruction for subtract, for all the other ones? Probably not so. Okay, because if one works, the other one works about the same way. But that's basically how I would study for this class at this point, because if I just turn all of this into text, it's going to be just as cryptic, if not more, but compared to interactively showing you what components are controlled how by the ROM. Is that okay so far? So that would be something that it's good to do within these few weeks, okay? Because at some point we're going to look at this and go like, okay, maybe we are not so concerned about the internal mechanism anymore, and instead we'll just focus on how do we write programs in assembly so that the output or the behavior of the assembly language program would resemble some C code. Okay. So are we still okay so far with this? Okay. So now we go back to our notepad here. Okay, so we go back to this and we say, okay, so how do we do this part here? This is a conditional statement, and we don't have conditional statements in assembly. We have compare, so we can tell whether a particular register is less than another register or equal to. We can determine that as well. We have unconditional branch instructions, and somehow we have to do this. If A is less than B, then else do something else using those instructions. So what do you think?
Compare A and B.
So compare is unavoidable. We definitely want to compare. And a compare instruction is the same thing as a subtraction, except the result of the subtraction is not stored. In other words, we go through the same commotion of subtraction with the compare instruction.
So does it just trip the flags then, or?
Yep, it will definitely affect the flags. Okay, so now it is a good time to remember what flags are we affecting. Okay, so we are affecting, this affects all the flags that we talk about. The carry flag, which is acting as borrow in this case. The Z flag, which is indicating whether the result is 0 or not. The overflow flag, which means whether the sign flag is correct or not. And then the sign flag itself, which is the most significant bit of the result. And also the L flag, which is the exclusive OR between the sign and the overflow flags. Okay, so all 5 flags are affected by the compare instruction. So now the next instruction is going to be a conditional branch instructions. Okay, so jump blah blah. Okay, to where do we want to branch? Now remember, you only have so many conditional branch instructions. Let's go ahead and take a look at the conditional branch instructions, which is in the spreadsheet and also in the assembler manual. So when you look at the branching or the jump instructions, you have the unconditional branch instructions, which are changing the program counter directly, so that the next instruction or the continuation of execution will continue to whatever the program counter is. The only difference between these two, jump X versus jump I, is jump X allows you to use a register to specify where to continue execution, as opposed to jump I, which is using an immediate, which is a constant, to specify where you want to continue execution. But it's unconditional. In other words, if we execute a jump whatever instruction, it will continue execution at that other point. Doesn't seem to be what we want to do with the if thing, right? So with the if thing, we have to use one of the other branch instructions using the carry flag to determine whether to branch or not. So when you look at the description of this, it says if the carry flag is a 1, then we want to use register X to update the program counter. Otherwise, we use the program counter to update the program counter, which means we're not changing the program counter. The next one is about the same, except we're using the immediate constant to change the program counter. But the most important part here is whether to change the program counter or not depends on the carry flag. If the carry flag is set, then we change. If not, we do not change the program counter. This is your only mechanism of branching. Yep?
Could you explain the difference again between the two?
Between the two?
Yeah.
So with X is representing a register, which means you can either pre-compute a value into one of the 4 registers, or you can use LDI to put something definite into one of the 4 registers and then use it here. So that would be, so JCX would be, only has 4 variants, JCA, JCB, JCC, and JCD. The second one, which is JCI as the instruction, as the mnemonic itself, and then the second I is an immediate. So you can actually specify a number. If you know exactly which location you want to jump to, if the carry flag is set, you can just say 6, 18, or whatever. You can also use a label. So is that okay so far? Okay. We also have JL and JLI. Okay, so the last 2 here correspond to the L flag. So now we go back to the code here. Which flag should I pay attention to? If you do not know, you have to ask me a question.
Carry flag, right? Maybe
Well,
use the carry flag.
you can use the carry flag, but only if you're dealing with unsigned values. So now it is basically, you know, if you have a question in your head earlier and you say, I'm not sure because text never said, you know, whether A and B are storing unsigned versus signed value, that would be the right answer. Okay? You know, having that question in your head, you're like, I'm not sure because it could be one of those 2, but text never said anything about whether A and B as registers are storing signed versus unsigned values. That is the right line of thinking.
That would be the L flag? L flag?
Can be the L flag if, but only if A and B are storing signed values. If A and B are storing unsigned values, you have to use the C or the carry or the borrow flag. Is that making any sense? Okay. So in order to determine which one we have to use, I have to tell you whether it is unsigned or not. If I say unsigned AB, then you use C here. If I say int, you have to use L here. What's the difference? I mean, 0, 0, so 0 is less than 1 all the time, whether it's signed or not, so why do we care? What if you're comparing 1, 1, 1, 1, 1, 1, 1, 1 as register A to 0, 0, 0, 0, 0, 0, 0, 0 as B? Would that make a difference?
The sign flag might be different.
Yep, they would be entirely different. So let's check out why they're different. So we go to, oh, we can put it here. Okay. Signedness matters, and this is why they matter. So when you look at this, you say 0, 0, 0, 0. I think the other one is 1, 1, 1, 1. There we go. So we'll flip it. So we will do this subtraction, okay? And I think we know that the overall borrow is a 0. Okay, the end result is 1, 1, 1, 1, right? Okay, don't tell me you have questions about why 1, 1, 1, 1 minus 0, 0, 0, 0 is 1, 1, 1, 1. Is that okay? All right. But what about the flags? The borrow flag is a, did we have the borrow? Nope, so that's a 0. What about the 0 flag? The 0 flag is a 1 if and only if the result is a 0. Did we end up with a 0? Nope, so the 0 flag is going to be a 0. What about the sign flag? Is the result having a 1 as the most significant bit? Yes. Okay. And that's a 1. What about overflow? Is the sign of the result making any sense? In other words, if you look at 1, 1, 1, 1 as a signed value, which is -1, is the sign of the result correct? Making any sense? Yes. you subtract a non-negative quantity from a negative quantity, you end up with a negative quantity. Makes sense to me. If it makes sense, overflow is going to be a 0. Okay, very good. So if the sign is a 1, overflow is a 0, what is L? Which is the exclusive OR between those two? It is a 1. Very good. But the most important part is you can see the borrow flag and the L flag do not agree. Which means depending on whether you use JC or JL, the program will behave differently. And that's based on whether A and B as registers are supposed to be storing signed values or unsigned values. Is that okay? Now this is a big difference, a big deviation from C and C++ coding, because in C and C++ coding, signedness is based on the type of a variable. Yep, go ahead.
Do we do anything to the processor where it will start reading bit values as signed or unsigned, or it just affects how we write the code?
It only affects which instruction you choose.
Okay, so the register is, the processor itself is always going to be the same?
Yes.
Okay, it just turns on how we're looking at it when we're writing
Correct.
the code? Gotcha.
Yep, and that's exactly what I was about to say.
Oh, sorry.
Is in C and C++, signedness is associated with how you declare a variable or typecasting, okay? But in assembly language programming, you know, when you say, okay, this location is going to store a value, we don't care whether it's signed or unsigned, it is a byte. A byte is a byte, okay? It's only 8 bits. It's only when you perform conditional branches, that's the only time in assembly language programming where you pay attention to go like, oh, is it signed? If it is, use L. If it is not, use C. Okay, so we have to be careful here. But since I specifically said they're unsigned here, we're going to use JC. Now JCI makes more sense than JC, because if you use JC, you have to load the location to branch to using a register, which basically uses up a register for no particular good reason. So JCI works really well, and JCI also allows you to use labels, symbolic names. So this way you can say, oh, okay, this seems to be a good location to branch to if A is less than B. Is that making any sense so far? Whoops. There we go. Is that making any sense? When A is less than B, go to location L1. And L1 is right here. It is the then branch. It's all good?
So
Yep.
when you do compare, it's going to be A minus B, and then that's going to be what's...
Yep.
Okay.
Yep. And that's also, you know, good to confirm with your own program. That a one-liner program is to look at the implementation of the CMP instruction and see which register is going to the first input of the ALU, which one is going to the second input of the ALU, and then see how those are internally wired to the subtractor inside the ALU.
Okay, cool.
Right. So that's a good question, because it really helps to understand how we can study for this class. Okay. All right. So the way the program is right now is after this CPR instruction, it will continue with the other CPR instruction, which is not good. So we need to jump around the else case. So you can put a halt here, okay? But I wouldn't put a halt here because that's a solution only if this program ends here. So if you have additional code, then you need to continue execution. So the better way to do it is to do a JMPI instruction to go to another label called L2, and we'll put L2 all the way over here, which is at the end of the entire conditional statement.
Don't you have to reach the else? How do you reach the else statement?
Aha! How do we reach the else statement? Well, the way it is right now is we do not have a way to get to the else statement. So what we need to do is to say, if we do not branch because A is less than B, let's do an unconditional branch instruction to the else portion. So this is where you can put L3, you know, to label else here. There we go. And let me see. Can people in the back still see the entire program? Because this shows more code, which is good, but if it is below the point where you can see it, then it serves no purpose. Is it still okay in the back? Okay. So is this program making any sense? Now, obviously, these label names are not very helpful, L1, what is it? L2, what is it? L3, what is it?
You can call it if.
Yep, you can change those labels. I would personally change L1 to the then label. Okay. I would change L3 to be the else label because it is marking the beginning of the else portion. And I would change L2 to end if because it is marking the end of this particular if statement. And they are case sensitive in the assembly. Any questions? If you guys want to read the entire program, well, this is the entire program, so we're good. It's just that we have a few comments, a few lines of comment at the beginning.
So the compare changes
It affects the flags. Yep.
behind the scenes, so whatever jump you use, you're going to use whatever flag to jump correctly.
Yep.
That's interesting.
So are we okay so far or not? It's good. Okay. So to run this program, I mean, if you already understand each individual instruction and you just want to know, okay, is this entire program as a collection of instructions working or not? You can just kind of let it zip through. If not, okay, I'm going to put a halt instruction all the way here at the end, just so that we have a way to stop the entire thing. On the other hand, if you're saying, okay, but I'm not really quite sure how JCI works, okay, then you may not want to run the entire program through just like zip through the whole thing, and you want to execute or single step through the JCI instruction by itself, just so that you can tell how it works. Okay, should we do that once to see how the JCI instruction works? Okay, good. We'll go ahead and do that. So before we do anything else, we can either hand assemble the entire program, which means you go to the. Let me show you where you can do this. So if you want to hand assemble something, at least once, just to understand the process, you can go to the opcode table spreadsheet, which gives you the base code of instructions, and also for instructions that require registers, it will tell you which register is controlling which bits of the opcode itself. So we have the compare instruction, we'll use it as an example. So the CMP instruction is right here, okay? So this is the CMP instruction, and you can see how the C code is, how I use the C code to represent it is x minus y, but the result is not stored anywhere. It's not like the other instructions where the result is stored, this one is not stored. So we are just going through the entire motion of doing the subtraction, but the difference is not stored. The flags are still affected, okay, so we're still changing the flags. But when you look at the opcode, it is 1110, which means the first or the most significant hexadecimal digit is going to be an E, okay, because it's 1110 of the way it is spelled out. But then the registers are XXYY, which means the first operand, whatever you specify as X, will control these two bits, XX. Whatever you specify as Y will control the YY bits. So in our instruction, because we are comparing A to B, register A is 0, 0, register B is 0, 1, so the actual opcode is going to be E1, because it is 1110, 0, 0, 0, 1. So it's actually E1 in hexadecimal. Okay? So that's how you hand assemble a program, which is quite painful because you have to go through this table, look up the binary code, and then figure out which registers, which bit, and so on and so forth. That's why we have the assembler. The assembler helps you with this. Questions of any kind?
Is there a...
Oh.
Now we have code blocks. We have code blocks in C++. Is there an assembly IDE/compiler that we could also use that you'd recommend?
You just need Notepad. I mean, this is,
But I mean, like, outside of all this, is there something else you recommend?
I do not have anything in particular. You might want to find an editor where you can specify your own syntax so that the mnemonics can be highlighted so that you can easily tell whether you're syntactically correct or not. Yep, go ahead.
How do the labels work?
how do the labels work? Okay, that's a good question. Okay, so how do the labels work? So if I were to hand assemble this program, let me do it by hand first. So if I were to hand assemble this program, I'm going to use another mouse pad on the side to illustrate that process. Okay, so if I were to hand assemble this program, then I would go to this location here and say this is location 00, and it has a byte of E1 in hexadecimal. I go to the next location, 01, and I look up JCI. So I go back to the spreadsheet, look up JCI, which is up here. This is JCI. Now you can see that JCI does not even have a spot to specify the I, so it only has an opcode of, in this case, is 44. Okay, so we specify 44 as the byte. Over here, well, as it turns out, anything that has an I as a suffix, like LDI, JCI, JMPI, and so on, the immediate constant is whatever byte is after the opcode. In other words, this byte here is going to specify the label. And let me switch back to here and switch up to here. So this byte is going to be the label then. But I haven't seen that label yet. It is not defined at this point, right? So what I'll do is I'm going to put a comment here and say to do resolve this label then, because I don't know what it is at this point. Okay, but it will take up 2 bytes. So the next location is now 03. Then I look up JMPI, and JMPI has an opcode of 40. And once again, I haven't seen the label else yet, so I have to say to do or fix it up later. If I see else, I'll come back and fix this. Is that okay? So now we actually encounter the label then, right? So the label then is corresponding to location 05. Exactly. So 03 belongs to the 40. 04 belongs to the byte that has the else value. So 05 is this location. So the moment I get to 05, I will say, oops, 05. So the moment I get to 05, I go back and say, oh, we needed to find out what then is. It is actually 05, and now it is resolved. That's how labels are used.
Okay, so the spreadsheet is doing that for us?
Yes. Yep, the spreadsheet is doing all of this for you. So it resolves the label references. It will also, convert the mnemonics into the opcode, and also figure out which register you're specifying and use it to tweak the opcode itself. Question? Yep.
One other thing. I'm not sure if it's needed, but you know how we had the ALU operations can change the flags? Is there a way to reset the flags to
All zeros?
or whatever their original state is?
Nope. There's no direct way to do it. You can craft a subtraction to affect the flags in a certain way, but certain flag combinations would not be possible. Yep. Is that okay? So there's no direct way to change the flags. They can only be implicitly changed or indirectly changed by arithmetic operations. Yep. So we still doing okay so far. I will not ask you questions like this in the exam, okay? Which is, really tedious and is not a good use of your brain cells.
Thank you.
we can solve more difficult problems.
Oh.
All right, so since that is not an issue, we just Control A, Control C, go back to the spreadsheet, but we have to go to the right one and paste. We have the whole program pasted. The comments would be fine, because everything, if you start off with // the rest of the line is not interpreted, just like in C and C++. So now we look at the output or the RAM file. We have the actual code. There are a lot of empty lines because the empty lines correspond to all the lines that has no instructions, which is fine. So we go download as comma separated, and we'll call this one find max. Find max. There we go. We switch back to Logisim, click the reset button, right click in the RAM, not the ROM. Okay, remember, all of these assembled instructions go to RAM. And this one is called find max. So right here, click open, and we got everything here. But right now the registers only have 0. They all have 0, 0, which is not a whole lot of fun. So we'll go ahead and doctor the register bank. So we go to here, we doctor this. We are comparing register A to register B, and this is unsigned. So how do you guys want to change it? Do you want it to branch or not? That's the question. Do you want it to branch? You want it to branch? Okay. So if you want it to branch, you want A less than B to be true. So, and it is unsigned, which means, if I keep this one, if I make this one 1, 5, 1, okay, 1, 4 is fine. We'll make the other one 2, 7. That will work because 1, 4 in hexadecimal is in fact less than 2, 7 as an 8-bit number. Is that okay? So this will guarantee that we'll actually perform the conditional branch. So we go back to main, and now we are ready to start the execution of this program. So we'll start with looking at the ROM, or the microcode engine. So we just Control T, and we should see the instruction here in the instruction register. And then in the next clock, E1 will become E10 in the microcode pointer, and we'll perform the compare instruction next. So Control T, and now we go to location E10. So now the output of the ROM is directing traffic to execute the compare instruction. So when we go back here, first question is, are we really comparing? Well, looks like we are using the ALU because the enable of the ALU is on. Okay, the ALU is active. If the ALU is active, we want to find out what is going to input 1 and what is going to input 2. Input 1 is coming from this demultiplexer, which is enabled, and the input is controlled by this wire, which is 0, 1. So register 0, 1 or register B is driving the output to input 1. Am I looking at the right thing? Yep. Okay. So this wire is telling us it is 20 in hexadecimal, and that would be 32. No, wait. It's 20. This is actually 20. I take it back. This is not in hexadecimal. This is actually 20, which is our 1, 4. Okay, so that's good. And this 20 is not that. This is controlling which register is serving as output 0. It is register 00 or the register A, which is good. That's our first one. Then we look at IN2. IN2 is selected by this mux here. This mux has a 0 for the select pin, which means input 0 is what is being the output of this mux. This is the output of this particular demultiplexer, which is enabled, which is good. But it's not enabled, it is selected. This is output 1 that is selected, which is good, and it's coming from output 1 of the register bank. Register bank is using register 01 or register B to output as output 1, which has a content of 39, and 39 is in fact 27 in hexadecimal. So that's good too. So are we doing okay so far? Sort of. Okay. Are we specifying a subtraction? I know the ALU is active. We're giving it something to process, but is it a subtraction? Well, for that, we have to look at the select of the ALU. The selection is 001, but how do we know that 001 is corresponding to subtraction? Well, we can always look into the ALU, and then we look at how the operation select is used. So you can see operation select 001 means we are using the input to feed the second output, which is going to the subtractor. So we know, in fact, it is actually subtracting. Okay. So if it is subtracting, do we get all the correct flags as the output? So we go back to logic sim, And we check the flags. Oh, we are no, we're good. We're good on time. So we look at flag outs or flags out. There we go. And for this one, you kind of have to look at how the bits are ordered. The first bit is, the least significant bit is a C. Second one is a 0. Third one is sign and then overflow and then L. So in this case, the C flag is in fact set. It is bit 0. So are we still doing okay so far with this? And you can see how boring it can get, when I spell out every single operation. But this is how things happen inside the processor. Okay, and this is how, quote unquote, you study, is to really look at this and make sure that you understand how these operations are carried out. Okay, but remember, the compare instruction is not even the most. It's not really the instruction that we are most concerned about. It's the JCI instruction. But yep,
is it
go ahead.
written somewhere what the flags or like what that?
Yeah, it's inside the. It's inside the ALU itself. So if you go into the inside the ALU, this merger tells you which bit is which bit. So this tells you bit 0 is carry, bit 1 is 0, bit 2 corresponds to, whoops, bit 2 is this one, sorry. Bit 2 is the sign flag, and then bit 3 is the overflow, and then bit 4, which is the most significant bit, is the L flag. Yep. So you can tell, you can examine the ALU itself to find the order. Okay, so the most important instruction that we want to illustrate in this case is not the compare instruction, which is relatively simple. It is this one. It's the 4-4, which is the JCI instruction. Jump if and only if the carry flag is set. Okay. So at this point, we are still in the fetch cycle of execution, which means we're just going to memory, get that byte into the instruction register, and then we use the instruction register to load the microcode pointer. Microcode pointer goes now to location 440, which is orchestrating the processor in the inside to perform the operation. Yes, go ahead.
So all the instructions are already on the ROM. All of
yes.
All the the zeros in between instructions, are those going to be
they're just unused.
Use those? Okay, so
yeah,
it's
they're
not
just
necessarily,
unused.
So it's not necessarily extra steps when we use those instructions.
Yep, correct.
Okay.
Because I reserved 16 slices of microcode for each instruction. As it turns out, I only need one for all of the instructions that I need to implement, which really shows you the difference between a CISC versus a RISC processor. In a CISC processor, a complex instruction set computer, the instruction set include instructions that are complicated enough that you will need like 4 or 5 even more slices of microcode to complete.
Okay.
But in the case of a RISC processor, each instruction is so simple that one single slice of microcode gets it done.
Can I get it done? Okay.
Yep. Okay.
Roll.
Sorry?
Roll.
I don't have roll sheet for this class.
Oh.
Not to. So now when we look at the output of this ROM, it is directing, okay, how do we execute this instruction? So this is kind of interesting because we know the program counter is going to be the center of attention because this is the one who's getting updated, the program counter itself. So now we have to say, okay, how are we updating the program counter? We know we are updating it because PCDN, which is going to the enable of this register, is a 1. So we know that we are ready to update this register on the next rising edge. The question is, how are we updating it? The input of the program counter comes from a MUX, a multiplexer, and the multiplexer has a select of 1, which means input 1 is what we use to update the program counter. Okay, well, that's not too hard to understand, but how come PC MUX is a 1? PC MUX is not coming out of the ROM directly. PC MUX is actually determined up here. It is the output of something. Okay, so how come it is a 1? Well, let's take a look at this MUX here. PC MUX okay, because it's a multiplexer of a multiplexer. That's why it's called PC mux mux. So PC mux mux is in fact coming out of the ROM directly. It is 0, 0, 0, which means I'm picking input 0 of this particular multiplexer to be the output. That is why PC mux has a value of 1. Okay? Cool. So when we go back to the program counter, that explains why PC mux is a 1, and that explains why we are taking input 1 to update the program counter. Well, that all that says is we are using the output of this other multiplexer to choose, you know, which one of its 2 inputs to use as the output. Well, this helps to choose, right? This is how we choose, you know, oh, we want input 1. But why is it input 1? It's because of this equation here. PC mux is a 1, register output 0 enable is low. So when you combine the negation of RO0EN and PC mux, then the AND gate outputs a 1, which in return becomes the selection of this particular multiplexer, so that we know we are choosing input 1 as the actual input to connect to the output. Is that okay? So now the question is, where is this going? Because that's actually what is specifying the new content of the program counter. So you track it down, you go like, okay, it can go from many places, but one of those many places is this one. And the other place is all the way to RAM. But which one is the answer, right? Because it can come from many places. So what you do is you track down this wire and you say, is this multiplexer driving this wire? No, because RO0EN is low. This particular demultiplexer is not driving any one of its outputs. Okay, it's just leaving the output floating. Then who's driving it? Well, it looks like this data can be driving it. Is it driving it? That's the next question. Well, when you look at the control signals to RAM, what are we doing? First of all, is RAM being used at this point? Yes. Selection is a 1. That means RAM is actually doing something. It's paying attention. Are we reading from RAM or are we writing to RAM? We're reading from because the LD pin is a 1. Oh, okay. So no wonder the output of this RAM is being used to control to hook up everything back to the program counter. Next question. How come we are reading location 02? Who said so? Well, let's look at the address bus, right? Because the address bus is what controls which location in RAM is being addressed. So who is driving the address bus? You track down the address bus, it goes all the way back to a multiplexer. The multiplexer has ADDR address mux being a 1, which means input 1 is connected to the output of this particular multiplexer, and address mux is a part of the output of the ROM, so that part is just determined by the ROM itself. And you look and go like, ooh, that looks kind of funky, because the program counter is specifying the address, and then we read from that location, whatever is at that location, we use that to update the program counter itself. But that accomplishes what we want to do, because the location where we want to branch to is stored as a byte right next to the opcode itself for JCI. So that's how it's done. Is that okay?
That's cool.
What if we don't want to update it to the other location? What if the carry flag is a 0? You go like, oh, then we have to restart the whole program, blah, 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 blah. No, we don't have to. If that's all you want to do is to figure out, what happens when the carry flag is a 0, go to the register bank, change these two to be the same thing. Oh, that won't work because the instruction to compare is already done, so doing this is not going to help. But we can still fix it. We can just go here. We just have to turn off the carry flag. The carry flag is bit 0, which means the 5 needs to become a 4. Okay. So we doctored the 1.4 to a 1. We doctored the 1.5 to a 1.4, and you can see bit 0 is now a 0, which means PC mux is going to be a 0. So you go back to the program counter. PC mux is now a 0. It would choose input 0, okay, which seems to be coming from the adder. It is coming from the adder. And then one thing, PC increment address mux. So it would. So this is correct, because if we want to skip that location that is containing the address to jump to, because if we don't do this, the next instruction that we are getting is going to be the address where we want to branch to, and we want to interpret that as an instruction. That would be wrong. So this is really just skipping the location that is currently storing the location that we want to branch to. Is that okay?
Can we clock it and see? Can we clock it and see?
Yeah. So when we clock it, you have to remember this is not really corresponding to the original program anymore, because we artificially turned off the carry flag.
So if once we clock it once, then everything will be updated though, right? So
Correct.
Change to?
So when we update, then PC would be 03. But when you look at the output of the program, 03 is corresponding to the next instruction. We skipped, we did not branch when we executed the JCI instruction, which is correct. That's what we want to do. Is that okay? So this means, what if you have a question about how the JCI instruction works, this is how you do it. You look at, first of all, you look at the wiring of the processor, and then you form a model in your mind of how it is supposed to work. Then you design a test program with 2 or 3 lines of code, as simple as it gets. And then you observe whether the program is doing what you think it should be doing or not. So that's how you study. Okay, you look at it, you look at the schematic of the processor, you form a model in your mind, and then you design an experiment to validate your understanding of the model.
Scientific methods.
Sort of. But that's how I understand stuff. I go through the same process whenever I need to understand something. Like right now I'm teaching cisp310, the first time I'm teaching that class. It's about PHP scripting. I knew a little bit about PHP before, but not really an expert in PHP coding. So when I try to figure out how do I use regular expression, I will read the documentation, I will read the specification and whatnot. I will form a model in my mind and go like, okay, this specifies this. I know regular expression, but the syntax of regular expression varies depending on the programming language. So I will form a model, and then before I put that code actually into the script that I need to write, I will write a 5-line program to test and make sure that my understanding is correct before I incorporate it into the actual program. So I think it works in this case too, okay? But it's just that some people might need to change the way they function in order to use this way of studying, instead of reading the book and try to memorize everything. Are we still doing okay so far? So let's single clock and find out what happens. Okay. So if I do a Control T, oops, make sure it's selected. So when I do a Control T, you can see program counter is now incremented to 3. And we are now at the very end of the conditional branch instruction. So the next clock will go to location 441, but 441 will only have a 2 followed by all zeros, which means we're going to go fetch the instruction at location 0003, which is the next instruction, the unconditional branch after the conditional branch instruction. Okay, just to be sure, Control T, we go back to location 000. And then we are fetching that instruction, which is the unconditional branch instruction with an opcode of 40. And then we'll decode it, go to location 400, and it's going to go through about the same thing. But this one does not look at the flags. This one just gets the next location, stick it into the program counter, and be done. Okay, so are we okay so far with this? Okay. So once you're comfortable with individual instructions and you say, but I just want to observe how the entire program works, Okay, that's fine. We'll go ahead and reset and reload the program. Okay, so reset, then reload the program, and also change the registers. Okay, so you might want to change the registers a little bit. Okay, and we'll have 1-4 again, which is 30, and then this is still 2-7, which is 39, because it's 32 plus 7, so that's 39 in decimal.
Isn't 1420?
Hmm?
Is it 1420?
Yeah, 1-4 is 20.
Okay.
Yep. And then we go back to main. So this time we're gonna kind of zip through the whole thing. So we go to simulate, we say click. Yeah, this is clocking at 4 kilohertz, so we are done. Exit. We go back to the register bank when we look at, and then we look at register C, which is supposed to be the maximum. It is in fact correct. And you want to do it the opposite way too. You want to put 2-7 in register A and then 1-4 in register B, and make sure that also stores the maximum of 2-7 in register C. But I'm pretty sure it does that. So are we good so far? Are we okay with all of this stuff? Yep.
I had to step out. Is this the program that we wrote earlier that we translated to?
Yeah.
Okay, cool. I
Yep.
just want to make sure.
Yep. That is exactly the same program.
I had a coughing fit. I had to step out.
Oh, okay. So are there any questions about this particular demonstration? Because from here on, your programming assignment, which I will make up, in just a moment, is going to look like what we just did today. I'll give you the C code, and you have to translate that into assembly code. And we'll start with something simple, where you can assume the values are already stored in registers, and you just write the code to do it. And then gradually we'll increase the complexity. In other words, what we'll do is we'll start to deal with nested control structures. This is not nested. This is just a conditional statement. And there's one single statement in each branch, which is relatively easy to translate. So we'll deal with nested control structure, like you have a loop with a condition inside or the other one around. And then we'll start to get into subroutines, global variables, local variables, parameters, return values, recursion.
Okay.
Yes, recursion. Yeah.
This just like loops will be like a bunch of jumps, like back to the beginning.
Yep. Yep, exactly. So there is one note that I just linked today for this class, because the other class got it linked last Thursday because they were just a little bit ahead of us. It is down here. It is called Assembly Language Programming. That's the name of the module itself. And the note is called Compiling Code for TTP. And you might think, oh, the instruction is going to tell us, there's a variant of GCC that will crank out, code for the toy processor itself. No. This is all about turning you into the compiler. So there's no GCC, that's just you. Okay? But we start off with something that's simple. Okay? We start off with something that looks like this. Okay? This is just a general C conditional statement where C is a condition, block 1, block 2 are just, it's just a chunk of statements. Is that okay? And what we want to do is, I call this flattening, because we're getting rid of the structure of this code. So we are flattening the structure code into something that has no curly braces. Because the curly braces is what make nested structure nested or nestable. So in this case, it's not nested anymore, but it has the same logic. Because when condition C is false, we go to label L1, which is the else label. We continue execution of the else branch, and it falls through. If condition C is true, not C is false, that means we are not going to go to label L1. It will fall through to block 1 by itself. Block 1 executes, then we'll go to L2 unconditionally. L2 is the end of the entire thing. So it will accomplish exactly the same thing, but there's no structure anymore. There are no curly braces anymore. Is that making any sense? Okay. And what if you have a loop? What if you have a while loop? if you have a while loop, you translate it. This is the structured code with curly braces. This is the unstructured code without curly braces. But do they do the same thing? That's the question. L1 marks the beginning of the entire thing, including the condition itself. And then when we check the condition, we don't check for the condition, we check for the negative condition. Because if the negative condition is true, then we go to label L2, which is here, which gets out of the loop. If C is true, not C is false. If not C is false, we do not go to label L2, which means we continue execution with block 1. After we execute block 1, which is the main body of the loop, we have an unconditional branch back to L1, which means we re-evaluate the condition. If the condition is false, we get out. If not, we continue, and so on. In other words, we are flattening the structure of a while loop. Do while loop, same thing, even simpler. So this is a do while loop, which we seldom use in most programs, but if you do have one, you translate it into here. Then you guys will be asking, where's the assembly code? Well, we're not ready to deal with assembly code yet at this point, but we are getting rid of the structure of structured programming. This is the one class where go-tos are needed. Because in assembly code, we cannot do that. But the point is, I'm trying to get everything to look like if some kind of condition go to some label. Because it becomes a conditional branch. So now the question is, how do we change the condition to be representable just using a single flag? The carry flag, the Z flag, the L flag, okay? If we can somehow change the condition to be represented by a single flag, then we can do a JCI, we can do a JLI, we can do a JZI to perform this conditional branch instruction. Is that okay? Do you guys understand why we are doing this step by step?
Can you say the last part one more time?
Okay, so what we want to do is to translate the C code into assembly code. In assembly, we cannot deal with complex conditions. The only thing we know what to do, we know how to do that is conditional to a single flag. So that's why we want to change. Eventually, we want that C to be as simple as, oh, we're just looking at the carry flag, or we are just looking at the Z flag, or we are just looking at the L flag. So we want to step by step reduce the complexity of the C code until everything can be done by a compare followed by a conditional branch instruction in assembly. This is the first step. Getting rid of while, getting rid of then else, getting rid of do while is only the first step. So the next question is, but what if C is complex? In other words, what if C is a negation? And well, if you want to get rid of the negation, you can make the code more complicated. If you want to go to L1 if and only if C is not true, you can always kind of do it the longer way, which is to say if C is true, we go to a continuation label L2. If C is false, you're not going to go to L2, which means you fall through to the unconditional branch to L2 in this case. L1, sorry. This code here is the same thing as this one here. But you got rid of the negation of the condition. In other words, we're sacrificing code complexity to get rid of operators. We took care of the exclamation point. What if you have an OR? What if you have a disjunction? If the original code has a disjunction, then it becomes two conditional branches. If C go, if D go, okay, that's relatively easy. If you have a conjunction to begin with, this is what you start off with, then it becomes this. It's a little bit more complicated because if you have conjunction, it is also doing the lazy evaluation or what we call short-circuited evaluation. If C is false, don't even bother to evaluate D, just go straight to the continuation point. If C is true, not C is false, do not go to L2. Instead, evaluate D. Because by the time we get to the second line, C is known to be true already. If D is also true, then we go to L1, which does what the original code does. If D is false, then we fall through to label L2, which is a continuation of whatever is following this. So these three particular sections is just saying, okay, how do we use more branches and more labels to get rid of the negation symbol, to get rid of disjunction, and to get rid of conjunction. What if C by itself is a disjunction? Then this C is a disjunction, then you have a negation of a disjunction. You can do one of two things. You can apply the code to deal with the negation. You can also apply De Morgan's law. Okay, you can apply De Morgan's law, so you're changing the disjunction, the negation of a disjunction to the negation of something and the disjunction and the negation of something else. So you can use Boolean algebra to your advantage to do all this. Simple reduction. Okay, this is a good section here, because these are the 6 usual comparisons that we encounter in C and C++. But in assembly, we only can deal with less than and equal to. So the question is, how do we deal with greater than when we can only do less than? Well, that's an easy one. You just flip the order, right? What if the original code has less than or equal to? Well, it becomes less than or equal to.
Yeah.
Well, that's exactly why it's called less than or equal to,
It's pretty neat.
right? But does that mean we have to compare again? Do we have to compare x, y twice to get this done? Nope, because the flags are all set in one single compare. So that means you have a JLI followed immediately by a JCI to the same label, wherever you want to go. Okay? Or JC, I, if it's unsigned, it's JCI. If it is signed, it's JLI. But nonetheless, the second one is always a JCI, because the C flag and the L flag and the C flag, they're all set exactly at the same time by the same compare instruction. You don't have to compare again. You just have to utilize the other flags that are also set. Okay. Greater than or equal to, change the order, easy one. Equal to is just that, because we have JZI to deal with that. And then not equal to, well, this one is kind of harder to deal with, because you have to kind of use the negation, which means you have to branch around the thing and then go to the place that you need to go. So there's no direct way to deal with not equal to, but the other ones we can do. And we are translating all of this. And this R, by the way, is a relation, which is less than, greater than, equal to, not equal to, and so on. And then we just translate that into something that looks like this. So if this is less than, then R is either C or L, and I forgot about the I, so it's supposed to be J something I. And here's an example. And then, of course, when things are nested, it becomes even more fun, because when it's nested, then you have to figure out the naming of the naming of the labels. If you have a conditional statement nested inside another conditional statement, then the labels called then, else, and if is not useful anymore, because you've got 2 conditional statements. So you have to figure out a systematic way to label those labels, the labels of your code, so that it is unlikely for you to accidentally use the wrong label. So in this case, I have a loop, and inside the loop I have a conditional statement. So when you look at the label itself, it tells you exactly where we are, or where we are supposed to be in the program, because it tells this tells me that I am inside, this conditional statement is inside the loop, because the label spells out exactly where I am in the map. Is it tedious? Absolutely tedious. Okay, but is it systematic? Yep, it is systematic as well. It beats using label L1, L2, L3, and then all the L's, because when you look at all the L's, you have no idea which one you're talking about. But when you look at this, it tells you exactly where it is supposed to be. Okay, like the label that I have just highlighted is supposed to be the end of the first conditional statement inside the first loop. What if I have a second loop in the main code? It has nothing to do with this. It's the first loop. Is that okay? So at the same level, it is the sequential number that matters, and then the nestedness has to do with stacking more and more terms, next to each other. Is that okay? So are you guys feeling sufficiently confident as a compiler now? Because that's exactly what a compiler does. Oh, lots of practice, yes. So I don't really have a homework assignment for you guys today, but it doesn't mean that you won't have a practice. I will give you a chance to practice. Okay, so figure out how to do absolute value, okay? Assume register A has a signed value already, and you are supposed to write the code to find the absolute value of whatever value is in A. You can store it back into A if you want to, or you can store it into B. Okay, but the important part is to figure out the logic to do it. It's going to be conditional because you don't want to flip the sign if A is already non-negative. But if it is not negative, you want to flip the sign. So the question now is, how do you flip the sign of a number when you're only allowed to use assembly language to do it? You can do 2's complement. You can also do 0 minus A. Okay, both will work. 2's complement can be done because we have bitwise not as an instruction, and then you just have to add 1 to it. We have the add instruction. So is that okay? So I'm going to leave that to you guys as a non-graded homework assignment, but nonetheless, between now and Thursday, I think you have enough time to get it done. On Thursday, remind me to go through the solution to that problem.
Wednesday.
Oh, Wednesday. Next time we meet, I think that's better.
There you go.
So next time we meet, we'll look at the solution of the code to find the absolute value of something. But meanwhile, I want you guys to work on it. Okay, so when we go to the lab, if you're going to the lab with me, we can work on that in the lab.